Venus is a world where the sun never sets on a landscape of melting lead and crushing shadows. It is the second planet from the sun and the closest planetary neighbor to Earth. For decades, it has been referred to as Earth's twin because the two worlds share nearly identical sizes, densities, and chemical compositions. However, while one developed into a garden of liquid water and life, the other became the most hostile environment in the solar system. Scientists study Venus because it represents a planetary scale version of what happens when a climate system moves beyond the point of recovery. By examining the Venusian atmosphere, researchers can better understand the fundamental mechanics of greenhouse gases and how they regulate the temperature of a rocky planet. This data is essential for climate modeling on Earth and for determining if distant planets orbiting other stars might be capable of supporting life. The history of Venus is a study in cause and effect. Scientific evidence suggests that billions of years ago, Venus may have possessed liquid water oceans and a climate similar to early Earth. Because it is closer to the sun, it received more intense solar radiation, which eventually triggered a catastrophic shift in its environmental balance. The process likely began with the slow evaporation of its oceans. As the water turned into vapor, it acted as a potent greenhouse gas, trapping even more heat from the sun. This created a feedback loop where rising temperatures led to more evaporation, which in turn led to higher temperatures. Eventually, the heat became so intense that carbon dioxide was baked out of the planetary crust and released into the sky. Unlike on Earth, where plate tectonics and oceans help reabsorb carbon into the ground, Venus lost its ability to recycle these gases. The result was a runaway greenhouse effect that permanently altered the planet. Today, the Venusian atmosphere is 90 times denser than that of Earth. Standing on the surface would feel equivalent to being 3,000 feet below the surface of the ocean. This immense pressure is enough to crush the hull of a conventional submarine. The composition of the air is approximately 96% carbon dioxide. This thick blanket of gas creates a global furnace, maintaining a surface temperature of roughly 900 degrees Fahrenheit. This temperature is consistent across the entire planet, regardless of whether it is day or night, or whether one is at the equator or the poles. High above the scorching surface, the planet is shrouded in permanent clouds of sulfuric acid. These clouds reflect much of the incoming sunlight, which is why Venus appears so bright in our night sky. However, the heat that does penetrate the clouds becomes trapped at the surface, unable to escape back into space. Our understanding of Venus is shaped by a few successful missions that survived long enough to transmit data. The Soviet Union's Venera probes are among the only human-made objects to have touched the surface. Most survived for less than an hour before the heat and pressure caused their internal electronics to fail and their structures to melt. We know for certain that Venus lacks a global magnetic field like the one that protects Earth. Without this shield, the top of the Venusian atmosphere is constantly eroded by the solar wind, a stream of charged particles from the sun. This process continues to strip away what little hydrogen remains on the planet, ensuring it stays dry and barren. Scientific data also confirms that the surface of Venus is geologically young. High-resolution radar mapping by NASA's Magellan mission revealed a landscape dominated by volcanic features and vast lava plains. There are very few impact craters, which suggests that a global volcanic event resurfaced the entire planet roughly 500 million years ago. There are, however, aspects of Venus that remain theoretical. While many models suggest it once had oceans, we do not have direct physical evidence of ancient shorelines. The extreme conditions on the surface have likely erased any such geological markers. Furthermore, some researchers have proposed the possibility of microbial life existing in the temperate layers of the upper atmosphere, where pressures and temperatures are more Earth-like. While chemical anomalies like phosphine gas have been detected, their presence does not prove the existence of biology. These remain topics of intense scientific debate and will require future missions to resolve. It is important to debunk the common myth that Venus is hot simply because it is close to the Sun. Mercury is significantly closer to the Sun, but is actually cooler than Venus. The difference is the atmosphere. Mercury has none, while Venus has the most efficient heat-trapping mechanism in the solar system. Another myth is that Venus is a volcanic hell of constant eruptions. While the planet is covered in volcanoes, we do not yet know if they are currently active or if the planet is geologically quiet. Future missions equipped with modern infrared sensors will attempt to catch a volcanic eruption in real time to answer this question. In a cosmic context, Venus serves as a mirror. It shows that the habitability of a planet is not a permanent state, but a balance of complex systems. The distance between a thriving world and a scorched one is a matter of atmospheric chemistry and the cycling of carbon. The study of Venus is not an exercise in fear, but an exercise in clarity. It provides the boundary conditions for what a rocky planet can become under extreme stress. It reminds us that while planets can be twins in physical stature, their life stories can diverge in radical, irreversible directions. The contrast between Earth and Venus is a testament to the unique conditions that allow our own world to remain stable. Venus is a finished experiment, a world where the climate has reached its final, most stable and most lethal state. It sits in our sky as a silent, brilliant neighbor, offering a cold and objective look at a possible future that we are only beginning to fully comprehend. The story of Venus is a reminder that the environment we take for granted is the result of a delicate equilibrium, one that has been maintained for billions of years, but one that is not guaranteed by the laws of physics alone.